At 07:16 UTC on July 5, 2026, seismic instruments on Russia's Kamchatka Peninsula recorded an explosion that sent a column of volcanic ash to roughly 12.2 kilometers above sea level, close to 40,000 feet. Within 20 minutes, the Kamchatkan Volcanic Eruption Response Team raised the aviation color code for Shiveluch volcano from orange to red, the highest level on the four-color international scale used to warn pilots that an eruption is underway or imminent, and that ash of significant concentration is entering the atmosphere. Satellite imagery from the Japanese Himawari 9 spacecraft, reviewed within the hour by volcanologists monitoring the region, confirmed a plume stretching more than 200 kilometers from the summit, with a portion of the ash cloud drifting directly over Elizovo Airport in the city of Petropavlovsk-Kamchatsky. That single explosion is the anchor for the question so many people are now asking. If a volcano on the far side of the Pacific can throw ash to the cruising altitude of a commercial jet, and if the wind that carries that ash typically blows east, how far east does it actually go? Does it stop at the Bering Sea? Does it stop at Alaska? Or does it keep moving until it crosses into Canadian airspace, and from there, potentially, deeper into North America? This is not a hypothetical question built on speculation. It is a question with a very recent, very concrete precedent, because in the third week of July 2026, ash from the same volcano did exactly that. It crossed the Bering Sea, it grounded flights in western Alaska, and satellite tracking showed it continuing on, drifting into the Yukon territory of Canada within about a day of the eruption that produced it. So the July 5th event that gives this story its number, 39,000 feet, is not an isolated curiosity. It is one data point in a months-long sequence of eruptions from a volcano that has now logged more than 300 formal ash advisories in a single calendar year. An extraordinary tempo of activity that has kept aviation authorities across the North Pacific, from Tokyo to Anchorage to Ottawa, watching the same mountain almost daily. To understand why this volcano keeps doing this, and to answer honestly whether Canada is at meaningful risk, it helps to start with what Shiveluch actually is, because it is not a typical volcano, and its behavior does not follow the pattern most people picture when they hear the word eruption. Shiveluch sits on the northern end of the Kamchatka Peninsula, in Russia's far east, roughly 450 kilometers northeast of the regional capital, Petropavlovsk-Kamchatsky. It is the northernmost active volcano in a peninsula that contains dozens of them, part of a chain along the Pacific Ring of Fire, where the Pacific tectonic plate is being forced beneath the Okhotsk plate, generating the heat and pressure that feeds this entire volcanic system. Shiveluch itself rises to about 3,283 meters, a little under 11,000 feet, and it is enormous in footprint, an andesitic volcanic structure with an estimated volume of roughly 1,300 cubic kilometers, which places it among the largest volcanic edifices on the entire peninsula. Geologically, Shiveluch is really two volcanoes layered on top of each other. There is Old Shiveluch, or Starry Shiveluch, an eroded stratovolcano that formed around 65,000 years ago and whose summit was long ago truncated by a wide caldera, a collapsed crater roughly 9 kilometers across, breached open toward the south. And there is young Shiveluch, or Molodoi Shiveluch, a much newer and much more active dome complex that has been growing inside that old caldera throughout the Holocene, the roughly 10,000-year geological period we are still living in. It is young Shiveluch that produces essentially all of the volcano's modern activity, and it does so through a process that geologists call dome-building eruption, which behaves very differently from the classic image of a volcano as a mountain that occasionally blows its top and then goes quiet for centuries. In a dome-building system, thick, gas-rich magma rises slowly through the volcano's conduit, and rather than erupting as a fast-flowing lava stream, it piles up at the surface, cooling and solidifying into a bulbous mass of rock sitting directly over the vent. This is the lava dome. It keeps growing, day after day, month after month, fed from below by fresh magma pushing up underneath it. The problem, from a hazard standpoint, is that this growing dome acts like a cork in a bottle. Volcanic gases trapped in the magma beneath it cannot escape smoothly. Pressure builds, and when that pressure finally exceeds the structural strength of the rock sitting on top of it, the result is not a gentle release. It is a violent, often sudden explosion that can blast fragments of the dome and pulverized magma miles into the sky in a matter of minutes. Volcanologists classify this kind of event as a Pelian eruption, named after Mont Pelée in Martinique, whose 1902 eruption, using the same dome collapse mechanism, killed nearly 30,000 people in the city of Saint-Pierre. What makes Shiveluch particularly difficult to forecast is that the timing of these dome collapse explosions does not reliably show up in advance on seismometers or on the tilt meters that monitor how much the ground around the volcano is deforming. Research on lava dome behavior has found that the rate at which a dome grows shows no consistent relationship to when it will explode or how large that explosion will be. In other words, the mountain can sit there looking stable, generating routine steam and gas plumes for days, and then rupture without a clean seismic warning beforehand. This is precisely why Kamchatka's monitoring agencies keep such a tight, continuous watch on the volcano, and why the aviation color code exists as a rapid public-facing signal, because for aircraft, the danger from an explosion like this arrives in minutes, not hours. Shivaluch's current eruptive episode is also unusual for its sheer duration. It began in August 1999, and as of this year has continued without a true pause for 27 years, making it one of the most persistently active volcanoes on the planet. Over that period, it produces roughly 0.015 cubic kilometers of magma annually, a modest but steady output that has been enough to sustain near-continuous dome growth punctuated by these periodic explosive releases. Since late December 2025, monitoring teams from the Institute of Volcanology and Seismology and the Kamchatka Volcanic Eruption Response Team have documented something structurally new at the summit. A second lava dome began extruding on the western portion of the crater floor, growing alongside the existing northern dome. By the end of February 2026, this newer western dome had actually grown taller than its older neighbor and was routinely producing ash plumes reaching 9 kilometers, about 29,500 feet, essentially as background behavior. Having two active domes matters because it means two separate pressure reservoirs capable of building toward an explosive release, either independently or in sequence. And volcanologists have noted that the collapse of one dome can physically destabilize the other, raising the odds of compounding events. This two-dome configuration is part of why 2026 has been such an intense year for Shiveluch specifically. To put a number on it, by July the 27th, the volcano had already generated its 305th formal ash advisory of the calendar year from the Volcanic Ash Advisory Centers responsible for tracking it, VAC Tokyo and VAC Anchorage. 305 advisories in under 7 months works out to more than one nearly every single day, an extraordinary tempo even for a volcano with Shivaluch's history. On that same day, July 27th, VAC Tokyo logged an ash cloud at flight level 350, 35,000 feet, which sits at the very ceiling of standard commercial cruising altitude, the airspace where long-haul jets flying trans-Pacific routes actually operate. The month had already delivered several major spikes before that. On July 2nd, an explosion at 8:54 UTC sent ash to 11 kilometers, about 36,100 feet. On July 3rd, at 20:05 UTC, explosions pushed ash to 10.5 kilometers, roughly 34,400 feet, and Cavert responded by raising the aviation color code to red, its highest tier. That plume was tracked by satellite extending 63 kilometers, about 39 miles, to the northwest of the volcano within an hour of the explosion. The color code was briefly lowered back to orange early on July 4th, after no further ash explosions were observed, only to be raised again the following morning when the eruption that anchors this story occurred. That is the sequence. The July 5th explosion at 0716 UTC, ash to 12.2 kilometers, just shy of 40,000 feet, with a satellite-confirmed ash cloud measuring 222 by 45 kilometers, positioned directly over Kamchatka's main airport and its largest city. Later in the month, the pattern continued. On July 16th, VAC Tokyo logged an ash cloud at flight level 230. On July 21st, around 22 ZOS UTC, or 2 in the afternoon Alaska time, Shiveluch produced what turned out to be the eruption most relevant to the Canada question, an ash plume reaching approximately 35,000 feet. This is the event that actually crossed the ocean. Here is what happened next, and it is documented not by speculation but by real-time tracking from meteorological and aviation authorities on both sides of the Pacific. The ash from the July the 21st eruption was caught by the jet stream, the fast-moving river of air several miles up in the atmosphere that circles the globe largely from west to east in the mid-latitudes of the northern hemisphere. Once volcanic ash is lofted high enough to enter that current, it stops behaving like a local hazard confined to the volcano's immediate vicinity and starts behaving like weather, something that gets pushed along a predictable path at speeds that can exceed 100 knots. In this case, the ash was carried east across the Bering Sea and directly into airspace over western Alaska. The consequences were immediate and measurable. The National Weather Service and aviation authorities issued multiple volcanic ash advisories covering the corridor from Tokyo to Anchorage. Alaska Airlines canceled 10 flights statewide on the Wednesday following the eruption, disrupting travel plans for roughly 1,100 passengers, according to a spokesperson for the airline. One of the specific flights grounded was Alaska Airlines Flight S-7011, scheduled to fly from Anchorage to Nome. David Fee, the coordinating scientist at the Alaska Volcano Observatory, part of the University of Alaska Fairbanks, explained publicly that Shiveluch's dominant wind pattern simply carries its ash eastward toward Alaska as a matter of routine geography. not as some unusual fluke of this particular storm system. The eruptive sequence that produced this particular ash cloud tapered off by Wednesday morning Alaska time, and by that same afternoon, satellite imagery showed the ash had drifted entirely across the state of Alaska and crossed into the Yukon territory of Canada. Fee noted that more eruptions from Shiveluch are likely going forward, given how active the volcano has been, though he was careful to add that another eruption does not automatically mean more ash is guaranteed to travel all the way to Alaska again, since the exact wind pattern on any given day still determines the specific path. So, to directly answer the headline question with the clearest evidence available, yes, ash from this exact volcano did reach Canadian airspace in July 2026, tracked by satellite crossing from Alaska into the Yukon within roughly a day of eruption. That is not a projection. That is what the imagery showed. The more useful and more complicated question is what reaching Canadian airspace actually means in practice, because there is an enormous difference between a diffuse, high-altitude ash cloud drifting over a sparsely populated northern territory and a scenario where ash concentrations are dense enough to ground flights, contaminate surfaces, or pose a direct hazard to people on the ground. This is where the 2023 precedent becomes genuinely useful, because Canada has been through a very similar version of this exact scenario before, and the government's own response gives a clear picture of how seriously or how mildly these events tend to play out once they cross the border. In the spring of 2023, Shiveluch produced its largest eruption in 60 years, a major Plinian event on April 10th and 11th driven by the same dome collapse mechanism described earlier, a lateral blast that sent a plume soaring to 20 kilometers, about 66,000 feet, spreading ash over an area of roughly 108,000 square kilometers, comparable in size to the entire island of Iceland. That eruption buried the village of Kluchi, about 50 kilometers from the crater, under 8.5 centimeters of ash, close to 3.5 inches, a genuinely severe local impact. In the aftermath, Transport Canada issued public updates describing its response, and those updates are worth quoting closely because they describe exactly the kind of institutional posture that would likely apply again if a comparable event unfolded today. Transport Canada stated it was aware of the Shiveluch eruption, described as occurring in what its bulletin called the Russian Aleutian Islands region, and reported that there had been minimal impact to Canadian air carrier operations. The agency said it was monitoring for any impacts to Canada's civil aviation transportation system and would continue taking necessary precautions to protect the traveling public. Behind the scenes, Transport Canada's Aviation Operations Centre was coordinating directly with NAV Canada's National Operations Centre, the body responsible for actually managing Canadian airspace and air traffic control, as well as with the Montreal Volcanic Ash Advisory Centre, one of the 9 regional centres worldwide, run in partnership with Environment and Climate Change Canada, that are specifically tasked with tracking ash clouds and issuing advisories to keep aircraft clear of contaminated airspace. Regular situation reports were compiled through Transport Canada's Situation Centre. And critically, within about a week, by April 17th of that year, the bulletin noted the ash plume had weakened to the point where it was becoming difficult to detect at all. That is the template. Ash arrives, is tracked meticulously by a coordinated network of Canadian and international agencies, causes minimal to no disruption for Canadian commercial carriers, because those carriers reroute around the advisory zones exactly the way Alaska Airlines did in July 2026, and then dissipates within days to about a week as the ash disperses, falls out of the atmosphere, and gets diluted below any concentration that instruments consider hazardous. The Montreal VAAC and NAV Canada exist precisely because this kind of transboundary hazard is a known and manageable part of operating a modern aviation system that shares an atmosphere with an active volcanic region on the other side of the globe. It is worth pausing on why volcanic ash is treated with this much institutional seriousness in the first place, because to a casual observer it might seem like dust that a jet engine, built to handle far more punishing conditions, should simply shrug off. The opposite is true, and the reason is chemistry, not just abrasion. Volcanic ash is not soft, powdery soot. It is composed of pulverized rock and volcanic glass, jagged microscopic silicate particles formed when magma is violently fragmented during an explosive eruption. When an aircraft flies through a cloud of this material at cruising speed, the ash is ingested into the jet engines, where combustion temperatures can exceed the melting point of the silicate glass in the ash. The particles melt inside the hot section of the engine, and then, as they pass further back through the engine and encounter cooler components, they resolidify, coating turbine blades and fuel nozzles with a glassy residue that can choke airflow, damage moving parts, and in the most severe historical cases, has caused complete engine flameout in flight. This is not a theoretical risk. It has happened to commercial aircraft before, which is exactly why the aviation industry treats any credible ash advisory as a hard no-fly instruction for the affected altitudes and corridors, rather than a mere caution. It is also, notably, a hazard that is largely invisible to standard onboard weather radar, which is designed to detect water droplets and storm clouds, not fine mineral particles, meaning pilots typically cannot see an ash cloud ahead of them the way they can see a thunderstorm. They rely entirely on the ground-based advisory system, the VAACs, satellite tracking, and coordinated air traffic control rerouting to stay clear of it. This explains why the practical Canadian risk from a Shiveluch eruption, even a dramatic one reaching nearly 40,000 feet, tends to concentrate almost entirely in the aviation sector, rather than in any kind of ground-level hazard for the Canadian public. Unlike the village of Kluchi, sitting 50 kilometers from an active vent in Kamchatka, no populated part of Canada is anywhere near close enough to Shiveluch to experience actual ashfall accumulating on roads, roofs, or agricultural land the way communities near the volcano itself can. By the time an ash plume has traveled the roughly 6,500 kilometers from Kamchatka across the Bering Sea, over Alaska, and into the Yukon, it has spent many hours dispersing, spreading laterally, and settling out of the atmosphere. What arrives over Canadian territory is a diffuse, high-altitude cloud, not a falling layer of grit. The primary risk that cloud poses is to aircraft that might fly through it at cruising altitude, and the entire system built around the VAACs exists specifically to prevent exactly that by rerouting traffic well clear of the advisory zone. That said, it is worth being precise about what has and has not happened, because the goal here is analysis grounded in the actual record, not reassurance for its own sake. The confirmed impact chain in July 2026 stops at flight cancellations in western Alaska, and satellite-confirmed ash drifting into Yukon airspace. There is no reported record in any of the tracking from Transport Canada, Nav Canada, or the Montreal VAAC of actual flight cancellations, ground stops, or airport closures inside Canadian territory tied to this eruption sequence, either in 2023 or in the current 2026 activity. That is a meaningful distinction. Reaching Canadian airspace and disrupting Canadian aviation operations are two different thresholds, and so far the evidence shows the ash has crossed the first threshold without clearly crossing the second, largely because the ash has consistently been diffuse and lower in concentration by the time it reaches that distance, and because Canadian and American aviation authorities coordinate closely enough on advisory information that carriers can reroute proactively before the ash cloud is even in Canadian airspace. Whether that pattern holds for future eruptions is where genuine uncertainty comes in, and it is honest to say plainly that nobody, including the volcanologists tracking Shiveluch daily, can predict with certainty how the next several months will unfold. What can be said is based on the mechanics already described. The volcano currently has 2 active lava domes rather than 1, a structural situation volcanologists have specifically flagged as capable of producing compounding or simultaneous explosive events. And one dome collapsing has the documented potential to destabilize the other. The eruptive tempo through July 2026, more than 300 advisories in under 7 months, is unusually high even by Shiveluch's own historically hyperactive standard. And the volcano has already demonstrated this year that it is capable of producing explosions reaching close to 40,000 feet, comfortably above standard commercial cruising altitudes, with the July 21st event proving that under the right wind conditions, that ash can physically traverse the entire North Pacific and cross into Canadian airspace within about a day. If Shiveluch were to repeat something closer to its April 2023 scale, a lateral blast reaching 66,000 feet rather than 40,000, the physics of ash transport suggests the plume would likely carry more material further, stay aloft longer, and cover a wider corridor, all of which would increase the odds of measurable impact, reaching not just Yukon airspace, but potentially further into Canadian territory, and would raise the odds of the kind of proactive flight rerouting and advisory activity that, while not necessarily producing outright cancellations, does add complexity and occasional delay to trans-Pacific and northern Canadian air routes. This is precisely the scenario Transport Canada's 2023 monitoring apparatus was built to watch for, and it is reasonable to expect that if Shiveluch's current sequence escalates toward that scale again, the same coordinated response, Transport Canada's Situation Centre, Nav Canada's National Operations Centre, and the Montreal VAAC working together, would activate again in essentially the same way it did before. There is also a broader pattern worth noting, because Shiveluch's behavior in 2026 fits into its own long geological history rather than representing something without precedent. The Global Volcanism Program's records show at least 60 large eruptions from this volcano during the Holocene, the current 10,000-year epoch, meaning large-scale explosive activity here is not rare on a geological timescale. It is close to routine. The 2 most catastrophic historical eruptions on record occurred in 1854 and 1964, both involving major collapses of the Summit Dome complex that triggered devastating debris avalanches down the volcano's flanks. The 1964 event in particular reshaped the mountain structure, carving out the scarp in which the modern young Shiveluch dome began forming in 1980, the very structure whose two active lobes are driving today's activity. Seen against that backdrop, the ongoing 2026 sequence, however intense by the standards of a single year, is best understood as a continuation of a persistent, well-documented pattern rather than a new or unprecedented threat. The volcano has essentially never stopped being active since 1999, and the current elevated tempo reflects the addition of a second lava dome, rather than any fundamentally new geological process. For anyone specifically concerned about air travel through this region, whether trans-Pacific routes connecting Asia and North America or more regional flights within Alaska and northern Canada, the practical takeaway from all of this tracked data is straightforward. The advisory and monitoring infrastructure already in place, VAAC Tokyo and VAAC Anchorage, on the front line closest to the volcano, the Montreal VAAC covering the Canadian side, KVERT on the ground, and Kamchatka issuing color code changes often within minutes of an explosion, and NavCanda coordinating actual airspace management, functions as a genuinely effective early warning and avoidance system. It is precisely because this system works, rerouting flights around advisory zones before ash concentrations become hazardous, that the July 2026 impact in Canada topped out at ash, drifting through Yukon airspace with no confirmed disruption to Canadian carrier operations, even as the same eruption sequence was actively canceling flights and disrupting more than 1,000 travelers just across the border in Alaska. The difference in outcome between Alaska and the Yukon in that specific event likely comes down to Alaska sitting directly in the most concentrated part of the plume's path at the moment it crossed the Bering Sea, while the ash reaching Canadian airspace had already thinned out further along its journey. Stepping back from the operational details, the underlying scientific story here is one of continuous, closely monitored risk, rather than sudden, unpredictable catastrophe. Shiveluch is not a dormant volcano that suddenly woke up. It has been erupting nearly without interruption for 27 years. What changed in the current cycle is the emergence of a second active dome since December 2025. And what that structural change has produced through the first 7 months of 2026 is the highest advisory tempo the volcano has generated in recent memory. More than 300 formal ash advisories, repeated red aviation color code alerts, multiple explosions reaching into or near commercial cruising altitude, and at least one documented case, the July 21st eruption of ash physically crossing the Pacific and reaching Canadian airspace within about 24 hours. It also helps to understand exactly how a volcanic ash advisory center actually does its job, because the process is more sophisticated than simply watching a satellite image and guessing where a cloud will drift next. Each of the 9 volcanic ash advisory centers around the world, positioned to give overlapping global coverage, combines several independent data streams before issuing a formal bulletin. There's the initial detection, usually from geostationary satellites like the Himawari series, that image the same patch of the planet every few minutes, allowing analysts to watch an eruption column rise in near real time and estimate its height, using thermal and visible imagery. There is ground truth data from seismometers and infrasound sensors around the volcano itself, run in Shivaluch's case by KVERT and the Institute of Volcanology and Seismology, which can confirm the timing and rough magnitude of an explosion within seconds. And there is atmospheric modeling, where meteorologists feed the estimated plume height, the estimated volume of ash injected into the atmosphere, and the current wind field at multiple altitudes into a dispersion model that projects where the densest part of the cloud is likely to travel over the following 6, 12, 24, and sometimes 48 hours. The advisory itself, the kind labeled with a designation like FVXX24 and a date-time group, spells out the volcano's position, its usual summit elevation, and the forecast movement of the ash at specific flight levels, giving air traffic controllers and airline dispatchers the specific coordinates and altitudes to avoid. This is why, even though volcanic ash is invisible to onboard radar, commercial aviation has managed to operate safely across one of the most volcanically active regions on Earth for decades, because the avoidance decision is made on the ground, well before any aircraft gets close enough to need to see the hazard visually. The economics of these advisories also matter to the broader picture, because they explain why airlines respond as aggressively as they do to what might look, from a distance, like a relatively small and temporary hazard. A single ash encounter severe enough to damage jet engines can cost an airline tens of millions of dollars in engine replacement, inspection, and aircraft downtime, to say nothing of the catastrophic outcome if an engine were to fail completely mid-flight. Weighed against that risk, the cost of canceling or rerouting a handful of regional flights, the 10 Alaska Airlines cancellations affecting roughly 1,100 passengers being a clear example, is a comparatively minor and fully rational business decision. Airlines operating in this region maintain standing protocols specifically for this scenario, built around the VAAC advisory zones, and dispatchers routinely reroute long-haul Pacific flights dozens or even hundreds of miles off their normal track to stay clear of an active advisory, adding modest fuel cost and flight time rather than risking an encounter. This is the same operational logic that would apply if a future Shiveluch eruption produced an advisory zone extending further into Canadian airspace than the July 2026 event did. NAV Canada and Canadian carriers would very likely absorb the disruption the same way, through rerouting and schedule adjustment, rather than through the kind of engine damage incident the whole system is designed to prevent. It is also worth placing Shiveluch's current activity in context against other well-known volcanic ash events that have shaped how seriously the aviation world treats this hazard. The 2010 eruption of Eyjafjallajökull in Iceland remains the reference point most people recognize. An eruption that, despite being relatively modest in raw explosive output, shut down large portions of European airspace for nearly a week and stranded roughly 10 million travelers, at an estimated economic cost running into the billions of dollars. That event fundamentally reshaped international aviation policy on volcanic ash, tightening coordination between meteorological agencies, engine manufacturers, and regulators, and establishing much of the advisory infrastructure now in routine use across the Pacific. Shiveluch has never produced a disruption on the scale of Eyjafjallajökull, largely because its plumes, even the larger ones reaching 60+ thousand feet in 2023, have tended to disperse over the sparsely trafficked North Pacific and Bering Sea corridor rather than over the far denser air traffic network of Western Europe. But the underlying hazard mechanism, fine silicate ash lofted to cruising altitude and carried long distances by upper atmosphere winds, is identical. And it is that shared mechanism, not the specific volcano, that keeps aviation regulators from ever treating an active redcoat eruption as a minor event, regardless of how many times a particular mountain has already done this before without a major incident. Looking specifically at what could change the current risk calculation for Canada, the clearest variable is scale rather than frequency. Shiveluch producing its 300th advisory of the year is, in one sense, less alarming than it sounds, because the overwhelming majority of those advisories describe modest, short-lived ash emissions in the 20 to 30,000 foot range that dissipate close to the volcano and never come close to intercontinental transport. What actually drove the confirmed Alaska and Yukon impact in July 2026 was a single, larger eruption on July 21st. And what drove the historic Kluchi ashfall in Transport Canada's monitoring response in 2023 was one exceptional Plinian-scale event far larger than the volcano's typical daily output. The pattern, in other words, is that Shiveluch's baseline activity poses essentially no cross-border risk at all, while its periodic larger dome collapse events, the kind tied to the destabilization of one or both of its current active domes, are the specific scenario capable of sending a plume far enough and high enough to matter outside Russian airspace. Monitoring agencies are watching precisely for the seismic, thermal, and deformation signatures that tend to precede these larger events, even though, as already noted, that data has historically given only limited advance warning before a dome finally lets go. So could the ash from Shiveluch reach Canada? The honest answer, based on the tracked satellite and advisory data rather than speculation, is that it already has, more than once, and the infrastructure built specifically to detect and manage exactly this kind of transboundary volcanic hazard. From Cavert's on-the-ground monitoring in Kamchatka to the Montreal VEAC and NAV Canada's coordination on the receiving end, has so far kept that arrival from translating into confirmed disruption on Canadian soil. Whether that holds through the remainder of 2026 depends on factors that are genuinely difficult to forecast with precision, chiefly whether the volcano's two active domes produce another large-scale collapse on the order of the 2023 event, and whether the jet stream on the day of any future eruption happens to point that ash directly along the same Bering Sea to Alaska to Yukon corridor it has already demonstrated it can follow. What is not in question is that the monitoring is continuous. The coordination between Russian, American, and Canadian aviation authorities is active and functioning, and the volcano itself, 27 years into an eruption that shows no sign of ending, remains one of the most closely watched geological features anywhere along the Pacific Ring of Fire.